Hello, hello. Let's see. Hello,
Good
Daniel.
morning.
Hello, Noelia. Oh, good morning. Good morning. Hello, Nikaya. Good morning. Good morning, Alyssa. Good morning. I just missed somebody. Good morning. Who did I just miss? Luna. Good morning, David. Good morning, Marina. Good morning. Someone else is coming in. Sorry. Who else is getting? Sorry. Hello. Hello. Good morning, Antonio. Good morning, Catherine. Good morning. Did I say Darina? I think I said. Sorry. Jennifer. Good morning. Hello. Yes. Hello. Jennifer. Good morning, Darina. Right. Sorry. Good morning, Alyssa. I said that. Okay. Hello. I think that I said Nikaya. I said Alyssa. Okay. Michelle is coming in. Okay. Good morning. Happy not weekend or something, or happy. Did I get it right? Yeah, is that it right? Okay. So I think so. We're like, you guys have done a lot of work. You're not going to get a new sheet tonight because we've got stuff to go over. You've done a lot, and hopefully, I think as of this moment, or at least as of a couple hours ago, anything you've done, you've gotten back. Hopefully, and actually should be the case, unless you handed something in the last hour or something. If you've turned anything you've turned in, I think, I hope, I believe I can say you've gotten back. So if that's not true, you should let me know in private chat or something. Um, all the We should soon start talking about a midterm exam, and we will, and it won't come without warning. It will come with practice and everything, but we're not quite there yet. So we're not going to talk about that today. Wait, sorry, more people coming in. Oh, cool. Oh, yeah, and homework. Right. If you submitted something maybe late last night, I might not have gotten to it yet. Yeah. And by the way, I think you're all on top of things. So, I mean, if you did submit something late last night, whatever it is, it's not late. It's cool. Then I probably haven't gotten to it yet, but you'll get it soon. Um, but I should check. Actually, to be totally honest, and as long as and good morning, Shitlali. Good morning, Melissa. Um, actually, to be totally honest, and I can check right now. I will check right now. The truth is that with homework 1 and 2, actually, I shouldn't say that. I think there are like 3 of you that haven't turned in 1 or 2. That's something you might want to start addressing, like just whoever you are, or you know who you are. And it's still, nothing is a crisis, nothing is too late. But actually, as long as I'm saying this, because I really do think this class is like, definitely nothing is too late for anybody. But I'm looking, excuse me. But yeah, I think there's 3 outstanding homework 1. So just privately, if you know who you are, you may want to reach out to. It's still definitely not too late. Like, don't be embarrassed. Even if I don't give you all 50 points, I'll give you a ton of points, and it'll be worth it for you to be able to move on. And same thing with homework 2. There's like 3 people outstanding. Maybe it's the same people. I'm not even looking. Um, Homework 3, I think there's 4 people. Okay, again, I'm looking at numbers here. I'm not looking at people. This is not a shame thing. Um, but then as far as I'm concerned, we're about to start talking homework 4 and 5 today. So you're not going to get anything new for a bit. If you have done 4 and or 5, you're totally on top of the game, ahead of the game, and like relax and buckle in, and like we'll go over it. We'll talk about it wherever you and stuff. And it's not too late to do it by any means. All right. So I think, and good morning. Sorry. Yes. Wait, I'm looking at the private chats. I mean, the direct chats. Yeah, yeah. No. Oh, okay. Thank you. Okay. So one of the people just acknowledged. Totally cool. I appreciate the acknowledgement. Like, I am here just to say, like, it just is to say that when you do stuff, it does count, and I do get it, and I see it, and it's definitely not too late at all. So yeah, I appreciate that at least one person in the chat just explained something to me. Cool. So you'll get it in. Just for all of you, just always do things in order. That's the only thing. Just don't try to do number 5 before you do number 4. Don't be ashamed to have to do number 2 before you move on to 3. Like, I did not understand physics until I did it the 59 millionth time for real, which means like, I get the luxury of looking at it again and again every year. You guys don't get that luxury, but you deserve it. That's how it works. Like, you get to look at things again. Anyway, so, all right, that's where we are with the homework, but I think I can start pressing on. Oh, and when will I post homework? Okay, good question in the direct chat. When will I post number 6? I was about to say this Wednesday night. Like, I'm not going to post it tonight. I'm not going to add it to anybody's pile for due for this Wednesday. I'll probably post it Wednesday, so we'll have time to catch up for. But then probably also right around then is when I'll start talking with you all about a midterm exam and where I'll cap off the homeworks Like, in other words, there'll be a finite, like the midterm exam will only cover through a certain number of homeworks. So there'll be like a pause in homework when I say, so homework 6 may be the last of them for a little bit, but that won't be till Wednesday. Yeah, I mean, that's a good, again, that was a question in the direct chat. You should not worry. You cannot look forward to any new homework happening tonight or tomorrow. Just like catch up for everybody, and it's brief for people who are already caught up. Sorry, I'm just looking, trying to. Someone just came in. Sorry. Okay. In. And I'm happy to keep taking questions like this, by the way. Like, I'm good because I think this class is on top of things, because I'm happy to say that we can get to the physics. I'm about to get to, back to physics, but that's just in absence of, but any questions you have like this, like when am I going to post what, or like, I don't want to get involved in the whole midterm discussion now. That's the one thing I'll say, let's not talk about right now. But other than that, any confusing thing or like what's going on with the game homeworks or this, you can put in the chat, or you can stop me now. I'm happy to stop. Like, we're not in a rush, I guess is what I'm saying. We're just on time to move forward. So I'm going to start. So you can think if you have questions or whatever, but I'm going to get to where we are. Right. Okay. Right. All right. Where we are. Where we were last. This is going to look like unfamiliar right here. I mean, it might look familiar from. Oh, sorry. Let me just look in the chat. Oh. Good morning. Good morning. Thank you. Oh, fair question in the in the direct chat. Fair question. Are there any major assignments assigned over spring break? Legitimate concern. The best way I can answer that, since off the top of my head, I'm not remembering exactly when spring break is, and I'm open to that input. I think the most honest thing I can say, but I never deliberately overload people with work during the break or something. The only question is how the exam lines up with regard to break. So the most honest thing I can say to this, let me say again, the question in the direct chat is, are there any major assignments assigned over spring break? The only thing that could potentially intersect with spring break might be if we're preparing for exam then. But we will know this Wednesday. This is now, I'll make this like a promise. This Wednesday, in 2 days from now, we will discuss the midterm exam, which means we'll pin down the date for it. Like, I'll probably come to you guys suggesting what I think the date is, but it wouldn't be for at least a week from now. I mean, you have to have time to prepare for it, and we do prepare for it. So on Wednesday, we're going to firm up and confirm the date for the midterm exam. You will have input into that, and we will resolve it. Then you'll tell, and you guys can incorporate your knowledge of spring break into that decision on Wednesday. So you can even prepare for that if you want. And I'm not being sarcastic. I'm dead serious. It's not something my brain can handle right now. Like, I mean, I actually find calendars more stressful than physics. But we will not just surprise you with a midterm that you don't get input into. This Wednesday, we will figure out the midterm. So please feel free to know when spring break is and bring that ready to the discussion, everybody, and we'll figure it out this Wednesday. Okay? I mean, for real. That's about okay. Fair question. Any other? Okay. So now, where are we? Well, we got to start catching up with these sheets. Like the sheets, the homework sheets, if you've looked at them, they start getting us into acceleration and various types of velocity, like known as midpoint velocity or instantaneous velocity. We've been discussing velocity a lot in class. First, we got this like one equation. We were looking like we were going to get into equation land. Then suddenly I dropped on you this whole Galileo principle of relativity thing, okay? Because it's really important to understand in English in all these various ways, like the summary. Yeah, in fact, the summary of where we are, of where we left off from last Wednesday. We're about to get physics law. Physics class, it's about motion. There will be laws of motion, of course. I mean, you've heard of them, and they will be put in equation form, and we're going to be, using equations more and more and more, right? But what I'm here to tell you or to remind you is that even before the laws come principles that govern how the laws are going to work. And that just like in the United States, there's a constitution, and the constitution does not tell people what to do. The constitution is not laws that govern people. It's laws that govern how laws can be written or not, like it, right? And it governs state governments governing people. It's a back document. That's what we're doing right now with Galileo's principle of relativity. We're actually learning the laws that say how physics laws are going to work. And specifically, if that's all way too abstract, specifically what we're really doing is trying to unpack the definition of velocity in more ways than one before we even move on and use it too much in equations with acceleration and stuff like that. Because all of physics from here on in is going to hinge on velocity and the relationship between velocity and acceleration. Like all of physics is about motion. Velocities are like our basic rate of motion. So just to remind you, so we have so far 4 forms of one basic idea, right? I'm not going to write them all again today because we did spend 2 days, but you are responsible. And we have 4 forms of one idea. The 4th form itself looks like 3 equations. Like hopefully you're looking at your notes, you see, or maybe I will write it again today, maybe if it becomes, but if you're looking for knowledge in this course, we have 4 forms of Galileo's principle of relativity now. The first 3 look like English. The 4th one looks like math. And it itself has 3 cases, Roman numeral 1, Roman numeral 2, Roman numeral 3. And each of those cases is like the 1 object case, the 2 object case, the 3 object case. All together, that is Galileo's principle of relativity, right? One second, sorry. Ooh, sorry, tons of people coming. Okay. Okay. What I'm doing right now, I'm not, as I said, I'm not going to write them all again, but they do keep coming up. They'll come up all the time. But I am rewriting the first one here, the first form, like the nugget, the actual kernel of this whole idea. And notice I'm writing it in slightly different words from the last time. Like I'm always going to, one of the reasons there's all these different forms is each time it's kind of like music, like each time we slightly say it a different way to try to point out a new implication or to try to clarify it more. Okay, and there's no exact word, like the words really matter because if you tweak the words too much, it's a totally different idea and it's a wrong idea. But on the other hand, the words are flexible. Like he never said this in English. There's no exact one like Bible quote of this. I mean, if there even would be, it wouldn't be in English, it would be in Italian or Latin or something. So what I'm saying here is I'm reminding you the idea that we're trying to establish, the idea that comes from basically thinking hard enough and looking hard enough at your feet and at the sky, thinking, wait, shit, am I moving or not through the sky? Like how, like what is moving, what is not? Am I sitting still and the sky is moving? Or am I moving through the sky and the sky's still? Like each idea is kind of weird when you think about it. And what's even weirder is the idea that you couldn't know it. Galileo is saying, actually, the end of the day, like at the end of the day, the thing about velocity is it is relative. Like you've heard this. I mean, there's a lot of right ways to understand this and a lot of ways to misunderstand it. But in the same way that we've heard the term relativity in association with Einstein and stuff like that, like it is the same word. We do mean the same thing here. We mean velocity is relative means velocity is only meaningful when you use it as a comparison between 2 objects. It's never meaningful, at least not in a science. It's never meaningful as just a description of one object. So I can't say this enough, because if you really get this idea and you really take it seriously and you're really willing to believe this idea, even in times that it doesn't seem convenient or expected, then you can do physics and you can do sciences so much more powerfully, first of all, than you'd ever imagine. But second of all, then you get science in a way that will show you that all the math and all the stuff that looks hard about this is the easy part. Okay, the math is the easy expression. I'm telling you, like, it'll look more mathy for those of you who want it to. It really will, especially physics 204. And I have announcements about that, by the way. Don't let me forget. If you get bored, we can talk logistics about physics 204 also, like what's happening next semester. I'll do that. But anyway, it's going to get more mathy. I promise. For those of you who want it to, it will. For those of you who don't want it to, it will. But I also promise you, having gone through the forest of the math and the physics and back, and been just as scared of it as some of you might be, or just as hating of it as some of you might be, I'm telling you that what's actually hard about physics is really believing in this concept, even when it doesn't feel like applicable or interesting. The concept is that velocity is relative, means it's like whenever anybody asks how fast is something going, it's like asking how taller is my sister. Like seriously, like how fast is like the word taller. It's not like the word tall. Like it's really easy to think that fast is a word like tall or something, like it's like an adjective or something. No, it's like the word taller. It's like I cannot walk up to you and say, guys, for 100 points of class participation, how taller is my sister? You'd be like, what? How spazzy is your English? Like, what? How taller is your sister? That doesn't even make any sense. Like, literally, that does not make any sense, right? It wouldn't. I can't say how taller is my sister. I can say how much taller is my sister than my brother, right? Or I could say how much shorter is my sister than my brother, or it could turn out that they're the same height, whatever. But if I'm going to use the word taller, there has to be two things involved, right? Like I know it sounds completely obvious, but what I'm here to tell you is it's sometimes obvious, but sometimes not, that speed, motion is the same way. You cannot talk about the motion of a thing without talking about it in comparison to another thing. And that's the way physics is going to, and our job in physics from here on is always to decide which thing we're comparing to what. Because what this principle says is that the laws are always the same, no matter which thing you are. If you're going at a certain constant velocity, the laws are the same as if you go at any other constant velocity. So whether you're actually going that way and the other person's sitting still, or the other person's going that way in the opposite direction, you're sitting still, that is not anything that either one of you can ever experimentally resolve or decide or declare. You're going a certain speed compared and motion direction compared to her. She's going the opposite direction, the same speed compared to you, and both truths are true. And that's the end of it. Okay, that's what the relativity principle says. It says velocities are relative. We can say it a million different ways. We're going to it, but that's a principle. But notice it's restricting. Now we're about to get to the homework. And sorry. And okay. So one example of that principle. Sorry, I have to say this. One of the questions on the homework, on the train of thought homework. Okay. Because like when I don't know if some of you believe this or not, what I'm saying, but I am saying like you can't like, so the answer is like, is the train actually moving? No, the answer is wrong question in physics. Is the train moving relative to the subway station? Like presumably, yes. Is the subway station moving relative to the train? Yes. Can you say that the train is stationary and the subway like is moving to the North Passage? Yes. Can you say that the subway, like all of those are equally true is the answer for real. You can't say one, but then that means, and some of you believe that all along, or some of you maybe believe that now, or so, I don't know what, people think, but one thing that really tests whether you really buy that or not is in that train of thought assignment. And again, this has nothing to do with points or grades or anything, but just one interesting question in there. Cause like there's a lot of research behind that survey of questions. One question in there, it says like, are you getting closer to, it asks you like early on, it says, are you getting closer to 59th? Are you getting closer to 14th Street? It says. And a lot of you put like, yes. I mean, a lot of you put like not enough information. I don't know, all of which is valid, but assume for the minute that you're like, yeah, this train is moving at this point. I think the train is moving. So you wrote, yes, the train is getting closer to 14th Street. Okay. Then a subsequent question was, is 14th Street getting closer to the train, right? Or I don't even know if it was about train. It was like, are you getting closer to 14th Street? And then the subsequent question was, is 14th Street getting closer to you? Okay, the one thing I want to say to the whole class is, from here on, if we're going to do physics, what physics is saying is that if you say, yes, I'm getting closer to 14th Street, then you have to say 14th Street is getting closer to me. Like, I'm not, this is not a critique of what, but like, that's the nub of just that pair of questions. Maybe you're not getting closer to 14th Street. Like, I don't know, maybe the train is sitting still. Like, I don't know. But if you're ever in a situation where you feel that you are getting closer to X and you have evidence for that, well, you can say that. You can say I'm getting closer to X. Like saying I'm moving relative to X. Just as equally, you can say X is getting closer to me. If one is true, the other has to be true. They can't, or they're both false. Like that is the relativity of velocity for what it's worth. So if you say I'm getting closer to 14th Street, then 14th Street is getting closer to you. And you might say, a big part of us wants to say, wait, you're going to go like that, Yaverbaum? Like you're saying the streets are now like moving to the subway. You're going to play like that, Yaverbaum? Like, okay, if that's your hokey pokey world where streets are moving to subways, like you might say like, all right, I get Yaverbaum how you could picture it that way. But you're telling me that that's like as validly true as saying that the subway is moving past the streets? I'm saying, yeah, it is as validly true. It's not just the way I want to look at it. Like, think about it. It is just as validly true, because if you think it's validly true to say your subway is moving past the streets, if you're like, that's the real deal, come on, like put aside the nonsense. Like we all know the streets are sitting there, they're fixed streets, like you can stand on them, you don't vomit. Right now I'm getting on a subway, the subway's moving past the streets, you say. So, and now I'm telling you as a physics teacher now, I was saying post Galileo, we say, well, if you believe that the subway is going past the streets, then you also have to believe just as validly that the street is going past the subway, like the other way. Like they're both exactly as true as the other. Any experiment you would do would like, you're going to get home, whether you want to say you got to home or home got to you. Either way, they're both valid. And you say, well, if you want to play that game, like I can get it right on your exam, Yaverbaum. Okay, if you want to say that physicists have this like cool, like we're all on drugs, so like we say the street's moving to you, you might say I can get that, but still that's like dumb. That's like goes back to like I can accept my third grade teacher telling me that the earth is like, but that's the thing, man. Like that's the thing. If you think it's dumb, if you think the earth, if you think like, no, the street is actually sitting still, don't tell me that the street is moving past the subway. Well, then I'm saying, well, do you think that the street is moving past the sun? Like, are you buying that or not? And I'm not telling you that you should or shouldn't, but I'm saying, make up your mind somewhere. If you think truly, really, the streets are sitting still and anything else is a game, then understand you're saying it's a game to say that the streets are moving at 65,000 miles an hour past the sun. And fair enough. If you want to say the earth is the center of the universe, like okay, but understand that's what you're saying. Like, at any physics is saying at any given moment, you have to pick a center and know what your center is and go with that. Don't assume it is the real center. There is no real center, but at any moment you pick a coordinate. Okay, that's what physics is saying. I'm going to move, but all this only works. Here I go. We're about to like turn the page or turn this to the homework now. It's about to get practical or something, I hope, if anybody wants to like quickly go to the bathroom, because just notice the one constraint of all this, or the one like hook is, I'm trying to find a color to serve, is this business right here. And we all know this is true. What do I mean? I mean, like this whole thing of like, I could be going over, it could be going past me. That's all as long as things are smooth, right? Everybody knows that in an airplane, you can get fooled for a while and just be chill and be free to move about the cabin without your seatbelt and like not even feel that it's going 500 miles an hour, as long as the plane is cruising, right? Everybody does, I think, really know this in their body. And I'm telling you, this is real physics. This isn't just something that you've gotten used to in your head and like is irrelevant. This is real physics, that the elevator can fool you on its midway journey. Like once the elevator has taken off and then it's just cruising, you can turn to your friend and talk and forget, especially if it's a long enough ride, you can forget you're riding. Right? And if you were to stand on a scale, it would register your normal weight. Your stomach is not like when it's cruising. But when the elevator first takes off, or the elevator is coming in for a landing, like so to speak, when it's accelerating or decelerating, when it's changing its velocity, then all bets are up. Then your stomach feels it. Then if you were to like jump, like something weird would happen. And same thing with the plane. Like you have to fasten your seatbelt when it's taking off, when it's landing, when it's turning, when it's hitting turbulence, right? In other words, we have to start moving on in this class now because we know, wait, yes, there's different velocities in the world. And physics is now saying all those different velocities are not really different. There's no like special number 0 or something. They're all just relative velocity. But if you change your velocity, there's no illusions about that. That's called acceleration. That's called non-constant velocity. we have to start looking at that now, right? That's where the homework sheets are going. It's like, what about when you change your velocity? Okay. That, so we're, blah, blah, blah. So I'm going to right now just introduce a new equation. Hold on. Okay, so I'm about to, this is like a transition. I'm saying all of what we're saying now is like every constant velocity is like indistinguishable from every other constant velocity. And all constant velocities can feel like zero, and any constant velocity can be called zero compared to all the others, right? Like that's where, but now we have to say, well, okay, but what about when the velocity is not constant? What about when it's changing? Something's going on there. And that's called acceleration. Okay, so I'm going to say now in English, we're going to define something called average acceleration. This is about to be an equation, of course, but I'm just first writing in English, which we're going to define to be, rather than, well, okay, remember, one second. Okay, this is officially our second equation now. And this is I feel like, just like before, we gave out a sheet where it defined certain things and you had to try based on the definitions of the sheet. And we started talking about it. So like some of you start the homework before we talk, some at, same thing here. Like I'm now just expanding on the definitions that are given in that homework sheet number 4. This may make it easier for some people to even start. Like they might not have been able to start without this, blah, blah, blah. But the definition I'm establishing now is, all right, let's define, like, let's acknowledge that velocities can change. Just like positions in space can change during time, and we call that displacement, and we call it, when it happens in time, we call it velocity. Well, velocities can change in time, and we're going to call that from now on average acceleration. So just like average, so this is meant to be, this is our second equation. It is, yeah, it's our second equation. It's meant to be, it's very much meant to be a parallel, or like an analogy. It's meant to deliberately look just like our first equation, because we are taking the same idea and just extending it one like rate of change. So velocity is change in position per time. Sorry, excuse me. Average velocity is change in position per time. Average acceleration is change in velocity per time. In a way, that's all we need to know in order to do all of sheet number 4, which we're about to start going over the answers, right? In principle, if you want to just like plug and chug stuff, that's the equation you need, or the definition to do sheet 4. But I want to say, well, a couple more things about it before I actually get into sheet 4. This is meant to be a parallel, like I said, but the parallel raises something curious. Okay, so far we have this. Okay, this gets into something here. We have two equations so far as I'm concerned, right? We have average velocity is displacement over time, i.e. average velocity is change in position per time. Now we have average acceleration is change in velocity per time. Like it's meant to like refer to the top thing. It's meant to build off that idea. But now notice like average is something that you measure or that you refer to an interval, a segment, a duration, a region between 2 points. I believe we made definitions for this at the beginning of the class, and maybe if we didn't, maybe we should. Did we do? I'm almost afraid to ask. Did we define the word space and time and event in this class? Like space is the interval between two events that can be measured with a ruler. Time is the interval between two events that can be measured with a clock. An event is a point in space. Can anybody verify with I mean, it's not crucial, but can anybody verify that I've ever said that before? That and it would be notes from if no one has, we might want to pause and write this down for a second. But
I don't think you did.
really, okay. Thank you. I believe you. All right, I will do that right now. I will do that right now. But stop me if this looks familiar once I do. I'm going to give some definitions. So we've given definition of like X and Y, but this is all about space, time, and stuff. So if I've never defined space or time, that would be bad on me. So let me do that quickly right here. But I hope I have said to everybody, triple equal sign means defined as. I hope I've said that, or I'm saying it right now. Certainly, when I use triple equal sign, it means equal by definition or is defined as. Double equal sign means equal by observation or circumstance or discovery, or whatever. But all right, so space. Sorry. I'm gonna pause for a second. There's more to this, so I'm just gonna. Well, I'm gonna go to the next page. Tell me, you can put it in private chat or public. I would expect that I should be. I'm gonna go to the next page so I can keep writing, but I can definitely go back to this page or tell me if I should go. But I will be flipping back and forth for a second. Okay, now this is all. If indeed I've never, this is kind of a dump of information here, and I would. So I'm going to go back to the first pages. I'm happy to go back and forth. As I said, I would like. I mean, this is worth it. A lot of things with me are like, this would, if this didn't happen a week ago, it would have happened in a week from now. Like things can happen different times, but you definitely do want this somewhere in your notes or whatever. If we're studying space time, which we are, stuff through space and time, and we're studying it in a scientific, i.e., measurable way, like here's the ground, here's prior definitions to the principles and the laws that we're even trying to manipulate. Like when we, and by the way, these definitions I'm giving you now, I should make clear, these definitions do not come from Galileo or Newton. These definitions come from Einstein, for real. Like, and these are close to exact words now. I mean, not that he originally wrote in English either, but he did speak English ultimately. These are from Einstein from approximately 1905. But they sound, as everything in physics at the beginning, they sort of sound maybe obvious or maybe over, but what they're saying is this, okay, from here on in, space is the interval, the segment, the region, the space, like the nothingness, the gap between two events. Okay, space, when we think of space from here on in, we're thinking of interval, separation between two events. Now, before I go any further, I'm going to say it's a kind of separation between events. Before I even get into what events are, right? I'm saying space, Einstein is saying space is a separation between events. It's a gap between two things that we're going to call events. And in fact, before we go any further, we're going to say there's different types of separations between events. There's like one that we call space and there's one that we call time. And what's the difference between the two? Well, at some very, very deep level, why we all love to know. The more we do physics, the more we do actually look at space and time and care about what are they really, really, really. But nobody really, I mean, maybe God only knows what space, like I don't know what space and time really are. But one thing that's different, and they're very similar, but they're very clearly different. One way in which they are similar is that they are both space and time intervals between something that we're going to call events. a way in which they're different for scientists, for physicists, in a way that makes physicists like do their job differently from mathematicians or philosophers or whatever, is that the way we measure them is different. Like, it sounds totally dumb, but remember, everything has to start with measurement to make, this is all the birth of physics. So space from here on in is going to be the interval between two events that you measure with a ruler. Like, whatever you do with that ruler, that's what we call space. If you're measuring the interval between two events with a clock, then we call that time. Okay. Now, events are points in space-time. An event is something that is uniquely identified or described by 4 coordinates, like, as far as we know, like 3 spatial coordinates, because there's 3 axes of space, it seems, and 1 temporal coordinate, because it seems like there's 1 axis of time. So an event, okay, and by the way, all this, I know maybe it seems like, I apologize if this is a little bit of a, if I've never done this before, it'll help with where we're going with the, anyway. It's where we are right now. An event in physics terms, an event is not a Jay-Z concert. Jay-Z concert is not an event. What is an event is the very first moment of the Jay-Z concert, like when the lights go on. Okay, that's an event. Or when, that's an event. An event is a point in space and time. It's a point, like, so one location, it's like a Euclidean dot, and 1 moment is what an event is in physics. So the opening of the concert can be an event. The closing of the concert can be an event. This class is not an event. This class is a good or bad. It's a series of events. Like the first clap, there wasn't a clap, like the first time I blinked my eyes in the class, that's an event, okay? So events, so this is how we now start thinking, because remember, we're measurers. We're trying to think of the world in a way of space and time where we're going to be able to make measurements and predictions and stuff. So the world is now a grid of like lots of rulers separated by lots of clocks. I'm looking in the world. I always have a coordinate system, a grid that I'm imposing on the world, and like how I measure. So, and space from now on, like or time, I think I've mentioned this in the class before. When I use the word time in this context, it means like the time between the beginning of class and the end, like the duration. That's what we mean by time. If you say, what time is it? That's an event. What it is now. Like, that's not the way we use time here. Okay, so, but then so there's space. Space is an interval, time is an interval, events are dots. Now, to be even more specific, an event is a full 4 coordinate thing. If you just look at the spatial coordinates of an event, the X, Y, and Z coordinates, that's called its position. It's like where it happened. So a position is a point in space. Similarly, an instant is a point in time, right? So there's points in time, and between them are time intervals. There's points in space, between them are displacements, space intervals. The whole package together is called space-time, okay? Why am I saying all this? Like, we can still do homework 4. Like, why did I assign homework 4 without telling you all this? Because, of course, you can totally do homework 4 and homework 5, and you can do a lot of physics without literally having these words in your brain. But I'm spelling out these words to try to highlight something before I go any further. Well, I'm spelling out these words because Nikai told me that I didn't before. So no, but I'm spelling them out because it means right from the get-go in physics, we want to distinguish between, at any given moment, are we talking about, like, is someone asking us something about an interval between dots, or are they asking us about the dots? Because the thing is, from here on in physics, what we're going to acknowledge when we're talking about intervals are what we can observe and measure, see, feel, hear, touch, believe in, experience in the lab. Intervals, like you can measure, oh, this thing is 3 feet long. Oh, this data collection procedure took 3 minutes. Like, you can measure intervals of time and interval space. When you measure, you can relate to it. It's numbers that are real. You can get data. So intervals have the advantage that they're like real in the real world. You can literally say, I'm like 5 foot 8 inches tall or whatever, right? And you can check it with a ruler. But the minute you check my height with the ruler, or maybe you even notice this, the minute I say I'm 5'8", and then I started like, I'm 5'8", well, on a good day in heels or whatever, not really, like, oh, kind of close to 5. I'm like 5'8.5". Well, I'm like 5'8". What we realize immediately is, like, even if you put a ruler to me right now, what we're going to get is my approximate height, like to the nearest, like however good that ruler goes, to the nearest centimeter or whatever, right? We're not going to get my exact height. We're going to get a believable height that we can relate to, that we believe, because there's like a ruler involved. but it's going to be approximate. Definitely, if there's a ruler involved, like definitely, right? There's uncertainty because there's space between the marks on the ruler, no matter how close they are. They only go so far. So I only know down to the centimeter or the whatever. So intervals, here's the deal in physics. Sometimes we're talking about intervals, and those are measurable, believable, relatable, identifiable, like real, but they're always approximate. And so things like average velocity, like how far you went in a certain amount of time. On average, you went 30 miles an hour. Okay, believable, real, like means something, like again, clocks, rulers, but average, but it's an average, 30 miles an hour. You went 30 miles an hour on average. You weren't always going exactly 30 miles an hour. It's approximate. On the other hand, we have quantities in physics where we talk about actual points. This is now going to bring me back to the equation finally, okay? Like this is where I'm going with this now. Like if we go back to these equations, we only have two equations. But what's happening on the left side of these equations here, on the left side, we're making reference to averages, to interval, like average velocity, like how far he went in a certain direction in how much time. What we get on the left is an average. It's real, it's believable, it's like scientific, it's from instruments, but it is approximate, it's an average. On the right side of the top equation, it's talking about x and x naught. Like those are not, those are places, those are exact positions. They don't have a bar. Like notice on the right side, there's no bar on top of those x's. It's not average position, it's the position. Positions are like actual places, points. Well, we can't actually measure points like Euclidean points like that have like no dimension. They don't take up any space. We can't actually measure them. We can only analyze them and do things with them mathematically and logically and verbally. Like we can talk about points, we can't actually measure them. So they're a little abstract. But on the other hand, the reason we talk about them is because they're exact. They're not approximate because they're from math. Not so what I'm getting, like, so position is a point on the right side. Average velocity is an interval. Where am I going with this? I now really want to examine then this equation here. What this must be saying I'm just rewriting it. Like it looks like a nice, harmless, like, oh, I want it to look reasonable, harmless equation. Just changing it. Just goes, sorry, I'll stop talking soon, even though I always say that is never true. So one thing I'm supposedly doing right now, I'm giving you this new equation, average acceleration equals change in velocity per time. Like that is what I'm trying to say. But I'm saying the minute I say that, the minute we acknowledge, oh, velocities can change, and so now like there's acceleration, would just be the word for that concept of velocities changing. But the minute we like say that and we write it that way, we realize, oh, now we're acknowledging, we're saying velocities can change just like positions can change. I was standing over here, now I am standing over there. So I was displaced, I traveled, I had some velocity. Well, similarly, here we're saying you were going 30 miles an hour like a moment ago. Now you're going 60 miles an hour. So your velocity change and so what's your acceleration? Like, that's what we're saying now. But if we're saying that, then then apparently we're not saying your average velocity was blah, blah, blah a minute ago, and your average velocity is now. No, we're saying your average velocity, we're saying your rate of motion at that moment was blah. And at this moment now, it's something else. Like, we're suddenly now talking about velocities at moments, right? That's what this right hand must be implying. In other words, this is a different kind of, this is not average velocity. This is velocity at an instant, which we're going to call now instantaneous velocity. Like I'm saying, in short, before we even, like, I keep wanting to go on, believe me, in the class, just like I'm sure everybody wants me to. Like, okay, we got velocity. Let's move to acceleration now. But every time I want to move on, I realize, holy crap, velocity is a deep concept. Before we moved on, the first thing we had to realize with train of thought is velocity is relative. It's not objective, first of all. Like, velocity is a relation, not a property. That was the point of the last like 3 days. Okay, that's train of thought. Now I'm saying, wait, also velocity. Before we move on, we also have to acknowledge sometimes with velocity, we're talking about it over an interval. We're talking about average velocity sometimes when we put a bar over it, even though, in fact, that was the very first time we ever talked about it was that way. But sometimes we're talking about velocity at a moment, at a point. That's a different kind of velocity. It won't have a bar over it. It will still be measured in miles per hour or meters per second, but it is different. We're going to call this instantaneous velocity. Okay, so velocity is it's a rich idea. It has like sub ideas to it. Instantaneous. So I'm saying now there's this thing called instantaneous velocity. V is instantaneous velocity. Instant. And the first thing about it should be is super clear. The first thing about instantaneous velocity is it does not mean the same thing as average velocity. It's related, but it's not the same thing, right? So we have average velocity is displacement per time. We said that is not the same thing as average of velocities. Now I'm saying average velocity over some time interval is not the same thing as velocity at a moment. What is velocity at a moment? Well, what velocity at a moment really is, and this is what it said on the first page of all these sheets, velocity at a moment is average velocity. I mean, of course, it's related. It's built off it. It is the concept of average velocity, but in the limit, as your time interval that you're looking at gets smaller and smaller and smaller, or gets arbitrarily close to zero. In other words, I'm saying and of course you've all heard this before in a different context, but I'm saying, and yeah, secretly, if you're I'm bringing in derivatives now, right? But and that will make this easier for some people to understand. It'll also make it easier for some people to kid themselves into thinking they understand just because they're like swapping the calculus. And some people can cheat themselves, but it also will make it look harder to understand for some of you. But I'm here to tell you, no, maybe this will, what I'm about to say you might be able to use physics to make calculus make more sense to you, or vice versa. What I'm just saying is this: it's all about intervals versus points. Okay. What I'm saying to everybody, of course, this is going to start looking like math, but like we're in physics now, so we have time and imagine one axis of space. Like we're still in one-dimensional kinematics here, right? So you imagine one axis of time, imagine one axis of space, and events, and like, and there's something moving around that you're watching: a basketball, a tennis ball, a car, a rocket, whatever, a ballet dancer. You're watching something move around. But move around what? Well, that just means back and forth in some motion, like the number line homework assignment. Like you're just watching something go back and forth. What's all this curvy schmurvy business? Remember, this is like the curve of a graph that you make. I mean, like if you made a graph of this thing just going back and forth, it only has 1 degree of spatial freedom, we call x, right? It can go forward or back, up or down on the x-axis, while the clock ticks along the t-axis, right? So the thing doesn't move in a curve. We just have something moving back and forth. Like whenever this blue line is going down, the thing is moving backwards. Whenever this blue line is going up, it's moving forwards, right? And when, I think you follow this, right? Well, the thing is, if we pick any 2 events in the path of in the graph of this thing's motion, if we pick any 2 events, like here's when moment 1, here's moment 1 when the object was over here at x1, and then later here's moment 2 where the object was at position 2, right? If we draw a dotted line between the 2, if we draw the dotted straight line, like then I mean, you know where many of you know where I'm going with this. Wait, let me make this closer. Right. Yeah. Like, if I draw the dotted line between the dotted red line between these 2 events, the slope of that line is the rise over the run. And you're used to seeing that as y2 minus y1 over x2 minus x1. But here we happen to have x and t rather than y and x, right? But it means the same thing. It's all the same axes. So the slope of that line would be the rise over the run, right? But rise over run in this case is change in x over change in t. That is to say, rise over run in this case, rise over run on this graph is displacement over time, right? What am I getting at with this? I'm getting at, if some object was moving back and forth, the slope of this line is the average velocity of the object between those 2 moments in time, between those 2 points of space, right? Right? Like the object, if we look at an object going back and forth, some pattern, like the guy who's going back and forth in the number line in the first assignment, some random object that's moving freely, spastically, whatever, but all within 1 dimension of space. So just moving back and forth at various speeds and stuff. Between any 2 moments we looked, the slope of that straight line is the average velocity that the object moved during that interval. It's the average, because it's the total displacement over the total time. It's the total rise over the total run between these 2 points. That's the average. That's like how fast he would be going or she would be going if they were always going at exactly the slope or the rate of that dotted line. But that's the dotted line. The slope of the dotted line is the average. But if you want to know what that person or that object is actually doing at any given moment, right? Like if I look like right here, like right at that moment, the object was not going at the rate of this dotted line. Like right at that moment, the slope of the blue line is not the same as the slope of the red line. Or right here, the slope isn't the same, wherever you want to pick. Or right here, the slope of the blue line is not the same as the red line. If you want to know the slope of the blue curve at any given moment, right, what do you have to do? You have to, if you want to know the slope right here, then you want to get the slope between here and here, if you follow what I'm saying, right? That will be a better approximation of the slope at an instant. But if you actually want slope at an instant, that at one point, that would mean rise over run for 1 point, and 1 point doesn't rise and 1 point doesn't run. Like if you want to know how fast something's going right at a moment, it's kind of like taking a picture of a car while it's driving down the highway and saying how fast was it going right at this moment. Like, oh, you mean between 3 o'clock and 3:02 p.m.? No, right at 3 o'clock, how fast was it going? Well, fast to me means how far you get in a certain amount of time. If at 3 o'clock, like if you want to give me 3 o'clock to 3:01, I can tell you how far it went in that minute and divide. But you're saying, no, you want to know how fast it's going at 3 o'clock. So what am I supposed to do? So at 3 o'clock, he didn't go anywhere. At 3 o'clock, he was right there. Like I have a picture to prove it. How fast was he going at 3 o'clock means how far was he going at 3 divided by how much time passed at 3. Well, that looks like 0/0 to me, right? If someone's asking how fast is something going at a moment, then that's like asking how steep is this curve at a point. Well, a curve isn't steep at a point because a point doesn't go up or down. A point is just a point. And a car doesn't drive in a photograph. Like when no time passes, there is no motion. So what we're talking about is a limit. We're talking about, oh, I know what we're saying. We're saying if I want to know how fast the car is going at 3, it wouldn't, I could start by saying, well, how fast is it going on average between 2 and 4? And you'll give me a number and it's like kind of close, but not that good. If I ask you for an average, how fast is it going on average between 2:30 and 3:30? Now you're going to give me the answer that's closer to what I'm looking for. If I say between 2:59 and 3:01, like now I'm like looking at this graph, I'm saying if you want to know how fast something's going at a point, what you're really asking is how fast is it going between 2 points that are super close to that one? So close, like the closer they get, your answer is going to get better and better. If your 2 points get so close that they're just 1 point, then your answer is meaningless. It's 0/0, literally. Like if you just literally look at 1 point, that's 0/0. And here's my problem with that: 0 over anything is 0, but anything over itself is 1, and anything over 0 is undefined or infinity, right? So 0/0 every single time is either a contradiction or meaningless or redundant. But that's what it would seem to be if you ask how fast is a car going at this moment. It seems like we would say 0/0 unless we're allowed to say, oh, I get it. By this moment, if you ask me how fast the car's going at 3, what you really mean is like how fast was the car going on average between like 2:59 and 30 seconds and 3 and 30 seconds. Like, or if you want me to do a little better, I can do a little better. If I don't want to go perfect because then we're gonna get 0/0, but I'll go as close. Oh, how close do you want me to go? Like 3. Oh, okay. I'll go to 2:59 and 59 seconds to 3 and 1 second. And that's good enough. Oh, why is that good enough? How come you don't do it? Oh, because your measuring equipment only goes down to a second. Oh, so anything past a second would be a lie anyway, because your measuring equipment can't even pick it up. Oh, that's what you mean by a limit. Oh, I never understood this in calculus before because it didn't make any sense to me, because calculus was supposed to be math and math was supposed to be things that were perfect, and the limit sounded very not perfect and very weird to me. Here's what a limit is. When I say limit, next page, when I say limit, I'm saying Okay, this is what I mean by a limit. Like to me, so this is what we mean by a limit, and this is for me what then helps us understand what a derivative is, which is where this is all going. And I know it's 12, by the way. I know it's 7 minutes or 9 minutes, so this will be the wrap up shortly. And I'm sorry, I'm not totally on homework 4 yet. But when we say limit as t approaches 0, okay, or approaches anything, but if we say the limit of t as t approaches 0, or the limit of something as t approaches 0, yeah, we mean a time interval that's like getting closer and closer to 0. But what do we like? But in math, that always confused me because I didn't know you were allowed in math to say things like closer and closer, like sounded so vague or whatever. Here's what we mean. When we say the limit as t goes to 0, we mean that it's still an interval. It's not 0. It's still a space between 2 points in time. Okay. So it's big enough that we can call it an interval. And in fact, big enough, like finite enough, like real, that we actually can measure it. Like it could be a second or a millisecond or a picosecond. But as long as we have a clock that can handle it, then we're going to call it, okay, then it's not 0. It's like something bigger than 0. But if it's small enough, okay, if it's small enough that our measuring equipment can't handle anything smaller, okay, so in other words, uh, um, like, so another way to put it is small enough that we know the interval is there, but we cannot say that it's smaller or bigger than any other interval we find like that. Like it's too small. Like, in other words, it's in the space between gaps on, it's between ticks on a clock, or it's between etch marks on a ruler, if we were talking about space. I'll put it one other way. Well, in other words, right, like if you're a cop on the highway with a radar gun and you're trying to find out like how fast someone's going as they pass your radar gun, okay, you can't actually know how fast they're going at a moment. What you're going to do is see how far they get in a really short span of time. Let's say the short span of time is like a millisecond, right? So you divide how far they went divided by millisecond. So that's on average how fast they're going throughout that millisecond. That's what it is. On average, how fast they're going throughout that millisecond. But here's the thing, as long as millisecond is as low as the measuring clock goes, as long as there's no clock in the world or in the police force or whatever that goes down to femtoseconds, then that's what we mean by the limit as it goes to 0, because like there's no smaller interval than that. That's the smallest interval there is, and it's so small you can't say if there's 4 of them or 5 of them or 6. Like that's as small as the measuring goes. That's what we mean when we say in the limit as t goes to 0. We mean any smaller than that, and the measuring equipment can't pick it up. So so we can call it infinitesimal. It's like an infinitesimal slice. And then at that level, so if I know how fast you're going on average for a millisecond, but there's no measuring equipment in the world that can tell the difference between a third of a millisecond or a fifth of a millisecond, right? Then as far as I'm concerned, any moment in that millisecond, you were going that fast. Even if your speeds were fluctuating during that millisecond, if I can't measure half milliseconds, then for the whole millisecond, I have to give you that speed. That's what we mean by limit in physics, okay? It's the threshold of measurement. Therefore, and I know we're just about, therefore, from here on, I agree. Like this is the link between here and calculus. Like it'll either make both of them easier or I don't, that's what it's ultimately meant to do. I'm saying therefore, oh, I'm sorry. Like, therefore, just like in math, where you say derivative is slope, take it to the limit, right? Like derivative is rise over run, take it to the limit where run is as close as you possibly can get to 0 without it actually being 0. That's what we're saying here. We are saying, I guess, yeah, to summarize, I'm saying we actually have 3 equations then. We have, and this is where we'll stop today. We have this. We have acceleration equals change in instantaneous velocity and time. And what do we, sorry, and now we have a definition. What we mean by instantaneous velocity is the limit as time approaches 0 of average velocity. Like In other words, instantaneous velocity is the derivative of position with respect to time. It is rise in position over run in time taken to the limit. Right. Right. The definition of the derivative is the rise over the run taken to the limit as run approaches zero. When we change from delta, sorry, I'll just say delta in physics and math, delta means small but finite interval between two values of a variable, and D means so small it's infinite, right? D is just a substitute for delta. Delta meant difference or change, like it's delta y over delta x slope. When we change, and I really want everybody to see this, if you didn't see this in calculus before, which is highly possible because I didn't for years, but dx dt or dy dx just really means delta y over delta x. It just means slope. It just means rise over run, but in the infinitely small case. That's what it means. Right now, I just want to see this one cool question in the chat, and then we're going to hit it. Oh no, yeah, these equations are like graphs are one way to understand this, or one way for me to explain it in terms of to remind you of where derivatives come from in a way. But right, no, these equations, these are the four equations we have so far now. In fact, technically we even have, well, I'll leave it at that. But yes, these are used for everything. Yes. And that's a really good question. And I think, and class is just about that. That's a lot. I meant we will go straight into the sheet next time. I apologize, but again, there won't be anything assigned new for a little bit. And Wednesday we'll talk about midterm and how to do it in a way that works for everybody. But those equations are now, I mean, technically, I think we have three equations now. These are three separate equations that are used. It is true, it's much easier to plug and chug with the first two. Like using the third one is tricky. We'll talk more about it. But yeah, they apply not just for graphs. Okay. Okay. If there are no, I'm gonna just stay to make sure there's no questions ready, but if I'm good, if you guys are good, so if you just say goodbye before you leave, that would be great. But I'm saying goodbye. But goodbye. Thank you, David. Okay, bye, David. So cool. Anybody? Yeah, bye. Bye. Cool. So if you could just say goodbye. Bye, Dorina. Thank you. I appreciate it.
Bye, Professor. Thank you.
Bye, Catherine. Thank you. Bye, Nikaya. Thank you. Bye. Oh, that was Nikaya. Okay. Yeah, just I like the goodbye thing. Oh, bye, Yasmin. Thank you very much. Bye, Jennifer. Thank you. So cool. Bye. 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 So you guys good? Noelia, Luna, Kat, Ajia, good. Awesome. Good. You guys good? You guys good? Yasmin, Camilla, Ajia, you guys good?